Picture yourself driving down a highway at night, watching the headlights of oncoming cars pierce through the darkness. You instinctively speed up, feeling the rush of velocity, the sensation of conquering distance and time. But what if I told you that no matter how fast you go, no matter what technology you develop, no matter how much energy you harness, there is an invisible barrier waiting for you at the end of that road? A cosmic speed limit so fundamental that it doesn't just govern your car or even spaceships, but reality itself. This isn't science fiction. This is the universe showing you its deepest secret, and Richard Feynman called it the most beautiful prison ever built. Imagine waking up tomorrow to discover that every road, every highway, every possible path you could take has the same maximum speed limit. Not because of traffic laws or safety regulations, but because the very fabric of space and time refuses to let you go faster. You press the accelerator harder, you build a more powerful engine, you eliminate air resistance entirely, but the speedometer stops at the same number every single time. This is exactly what physicists discovered about light in the early 20th century, and it shattered everything we thought we knew about motion, time, and reality itself. But here's what makes this story truly remarkable. Feynman didn't see this cosmic speed limit as a cruel joke played by nature. He saw it as the universe's way of protecting itself, of maintaining the delicate balance that allows matter, energy, space, and time to exist in harmony. When most people learn about the speed of light limit, they feel frustrated, confined, as if nature is keeping us from reaching our full potential. Feynman felt something completely different. He felt wonder. He felt gratitude. He understood that this apparent limitation was actually the key to understanding why anything exists at all, why the universe doesn't collapse into chaos, why we can make sense of the physical world through mathematics and experimentation. Think about the last time you felt truly free, perhaps running across an open field or driving with the windows down on an empty road. That feeling of limitless possibility, of being able to go anywhere and do anything. Now imagine discovering that this freedom, this ability to move and explore, only exists because of boundaries you never knew were there. The speed of light isn't the walls of a prison, it's the foundation that makes the prison cell of reality stable enough for consciousness, matter, stars, planets, and life to exist inside it. Without this limit, there would be no inside at all. Have you ever really stopped to think about what speed actually means? Not just the number on your car's dashboard, but the fundamental concept itself. We measure speed by comparing how much distance something covers in a certain amount of time, miles per hour, kilometers per second. But what happens when you try to measure the speed of something that defines what distance and time actually are? This is where our everyday intuition starts to break down, where the comfortable world of common sense begins to crumble, and where Feynman's genius started to illuminate the deeper structure of reality. Most people think they understand speed because they've experienced it their entire lives. You walk at roughly 3 miles per hour. Cars typically cruise at 60 miles per hour on highways. Commercial jets fly at about 500 miles per hour. These numbers feel natural, scalable, infinite. If you can go 60 miles per hour, surely you can eventually figure out how to go 600, or 6,000, or 60 million. The progression seems obvious, limited only by engineering challenges and energy requirements. This intuition has guided human transportation for centuries, from horses to trains to rockets. But what if this intuition is not just wrong, but fundamentally, catastrophically wrong? When you throw a baseball, you expect that throwing it harder will make it go faster. When you drive a car, pressing the accelerator more gives you higher speeds. When engineers design rockets, adding more fuel and more powerful engines produces greater velocities. This cause and effect relationship between energy input and speed output forms the foundation of our mechanical understanding of the world. It's so obvious, so consistent in our daily experience, that questioning it seems absurd. Yet this is exactly what Einstein's special relativity did, and what Feynman spent his life helping people understand. Our most basic intuitions about motion are elaborate illusions created by living at extremely low speeds compared to the cosmic speed limit. The question isn't really whether the speed of light is a mental prison. The question is whether our minds are equipped to understand a universe where space and time are not separate, absolute quantities, but intertwined aspects of a single fabric that can stretch, compress, and curve. Can human consciousness evolve to navigate a world of moderate speeds and familiar objects, truly comprehend a reality where time slows down when you move faster, where simultaneity becomes relative, where the very concepts of before and after depend on your reference frame? Feynman believed we could, but only if we were willing to abandon our preconceptions and follow the mathematics wherever it led us. Let me take you back to the summer of 1626, when a Danish astronomer named Ole Rømer was doing something that seemed completely unrelated to cosmic speed limits. He was studying the moons of Jupiter. Rømer had been carefully timing the eclipses of Io, Jupiter's innermost large moon, as it disappeared behind the planet. He expected these eclipses to occur at perfectly regular intervals, like clockwork. After all, orbital mechanics should be predictable, mathematical, precise. But something strange was happening. When Earth was moving toward Jupiter in its orbit, the eclipses seemed to happen a few minutes earlier than predicted. When Earth was moving away from Jupiter, the eclipses appeared to be running late. Most astronomers of the time assumed this was due to measurement errors or unknown gravitational influences. But Rømer had a revolutionary insight. What if light itself took time to travel from Jupiter to Earth? What if those early and late eclipses weren't timing errors, but evidence that light had a finite speed? When Earth was closer to Jupiter, light had less distance to travel. When Earth was farther away, light needed more time to make the journey. Using the known diameter of Earth's orbit around the Sun, Rømer calculated that light traveled at approximately 140 sawags miles per second. This was the first measurement of light speed, and it was astonishingly close to the modern value of 186,282 miles per second. But here's what makes Rømer's discovery truly profound. He had stumbled upon the first hint that the universe has a built-in communication delay. Every star you see in the night sky is showing you its past, not its present. The sun you see is 8 minutes old. The nearest star beyond our solar system shows you events that happened over 4 years ago. The most distant galaxies visible to the Hubble telescope are showing us light that began its journey when the universe was young, billions of years before Earth even existed. Rømer had discovered that space and time are connected in ways that make instant communication across cosmic distances impossible. Imagine trying to have a real-time conversation with someone on Mars when the planets are at their farthest apart. You say hello, and 24 minutes later, you hear their response to something you said 24 minutes before that. You're not just separated by distance, you're separated by time itself. The speed of light doesn't just limit how fast you can travel, it limits how quickly information can flow from one place to another. This creates a fundamental structure to reality where cause and effect become relative, where simultaneity becomes meaningless across large distances, where the very concept of now becomes a local personal experience rather than a universal truth. 2 centuries after Rømer, physicists were still trying to understand the true nature of light. Was it a wave like sound moving through air? Was it a particle like tiny bullets flying through space? If it was a wave, what medium was it moving through? Ocean waves need water, sound waves need air, so light waves must need something too. They called this hypothetical medium the luminiferous ether, and by the late 1800s, detecting this ether had become one of the most important goals in physics. In 1887, Two American physicists, Albert Michelson and Edward Morley, designed what they thought would be a straightforward experiment to measure Earth's motion through the ether. If Earth was moving through a stationary medium that carried light waves, then light should travel faster when moving with the ether wind and slower when moving against it, just like sound travels faster with the wind and slower against it. They built an incredibly precise interferometer that split a beam of light in two directions perpendicular to each other, then recombined the beams to look for differences in travel time that would reveal Earth's motion through the ether. The result was completely unexpected. No matter which direction they pointed their apparatus, no matter what time of day or year they conducted the experiment, light always traveled at exactly the same speed. There was no ether wind. There was no stationary medium. Light seemed to move at the same speed relative to every observer, regardless of their motion. This wasn't just puzzling, it was impossible, according to everything physicists understood about motion and waves. If you're on a train moving forward at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees the ball moving at 70 miles per hour. But light doesn't follow this rule. Light always moves at the same speed, no matter how fast you're moving, when you measure it. Let me give you an analogy that captures just how strange this discovery was. Imagine you're standing on the side of a highway with a radar gun, measuring the speed of passing cars. A car approaches at 60 miles per hour. You jump into your own car and chase after it at 30 miles per hour, expecting to measure the other car's speed as 30 miles per hour relative to you. But instead, your radar gun still shows 60 miles per hour. You speed up to 50 miles per hour, and the other car still shows 60 miles per hour on your gun. You somehow manage to accelerate to 59 miles per hour, just 1 mile per hour slower than the car you're chasing, and incredibly, impossibly, your radar gun still reads 60 miles per hour. This is exactly what Michelson and Morley discovered about light, and it broke physics. Let's put this in numbers that really drive home the strangeness. Light travels at 282 miles per second in a vacuum. If you're standing still and measure a beam of light, you get 282 miles per second. If you're in a car moving toward the light source at 60 miles per hour, you still measure 282 miles per second. If you're in a rocket ship moving at 100 miles per second toward the light source, covering more than 500,000 miles every 6 seconds, you still measure the light's speed as exactly 282 miles per second. Even if you could somehow accelerate to 281 miles per second, just 1 mile per second slower than light itself, that beam would still pass you at exactly 282 miles per second relative to your reference frame. This invariance of light speed isn't just a curious property of electromagnetic radiation. It's a fundamental feature of space-time itself. What Michelson and Morley had discovered without realizing it was that space and time adjust themselves to keep the speed of light constant for every observer. When you move faster, your clocks slow down and your measuring sticks contract in exactly the right proportions to ensure that when you calculate speed, distance divided by time, you always get the same answer for light. The universe literally reshapes itself around you to maintain this cosmic speed limit. Please pause this video right here and tell me in the comments, have you ever tried to imagine what it would feel like to travel at 99% the speed of light? What do you think would happen to your experience of time, space, and reality itself? Don't just think about the physics you might have learned in school. Think about what it would actually feel like from the inside to approach the cosmic speed limit. Would you feel the universe changing around you, or would everything seem normal until you tried to communicate with someone who wasn't traveling with you? I'm genuinely curious about your intuitions here, because understanding how our minds naturally respond to these extreme scenarios helps us appreciate why Feynman's insights were so revolutionary. Share your thoughts below, and don't worry if your ideas seem wild or impossible. The actual physics is much stranger than most people's wildest guesses. And here's where we need to talk about why this matters for your daily life, not just for abstract physics. That GPS navigation system in your phone, it only works because engineers programmed it to account for the fact that time runs slightly faster on satellites orbiting Earth than it does on the ground. The difference is tiny, about 38 microseconds per day, but if GPS satellites didn't correct for this relativistic time dilation, your location would be off by about 6 miles after just one day. Every time you use GPS to navigate to a restaurant, find your way home, or track your morning jog, you're relying on Einstein's understanding of space-time and light speed to get accurate results. The cosmic speed limit isn't just an abstract concept, it's woven into the technology that runs modern civilization. This is where Richard Feynman's perspective becomes absolutely crucial for understanding not just what the speed of light limit means, but why it exists at all. Most physicists in the early 20th century saw Einstein's special relativity as a mathematical framework for calculating how measurements change between different reference frames. They learned the equations, applied them to solve problems, and moved on to other topics. But Feynman had a fundamentally different approach to physics. He didn't just want to calculate what would happen in various scenarios. He wanted to understand why the universe was constructed this way in the first place. Feynman's insight was that the speed of light limit isn't an arbitrary cosmic rule imposed by some external authority. It's the natural consequence of the universe having a consistent, logical structure. Think about it this way. If there were no universal speed limit, if you could accelerate forever and reach infinite velocities, what would that mean for causality? You could send a message to your past self. You could arrive somewhere before you left. You could create grandfather paradoxes and logical contradictions that would make it impossible for the universe to have a coherent, predictable structure. Let me walk you through one of Feynman's favorite thought experiments. Imagine you're holding a flashlight and you turn it on. The light travels away from you at 282 miles per second. Now imagine you start running forward at half the speed of light, about 141 miles per second. From your perspective, you're moving, but the light from your flashlight still leaves you at 282 miles per second. It doesn't add your speed to its own speed to reach 423 miles per second. This seems to violate our intuition about relative motion, but Feynman showed that this apparent violation is actually what allows cause and effect to work consistently throughout the universe. Here's why. If light could travel faster than its fundamental speed limit by inheriting motion from its source, then information could travel backward in time under certain conditions. Specifically, if you could send a light signal from one moving reference frame to another moving reference frame under certain geometric arrangements, the signal could arrive before it was sent. This would create situations where effects could precede their causes, where you could send messages to your own past, where the logical structure of reality would collapse into paradox and contradiction. The speed of light limit is the universe's way of maintaining temporal order. It ensures that cause always precedes effect, that information flows forward in time, that the sequence of events has meaning and consistency. When Feynman called it a beautiful prison, he meant that this apparent limitation is actually what makes freedom possible. Without the walls of the prison, the concepts of freedom, choice, causality, and logical reasoning couldn't exist. The speed of light isn't constraining reality, it's defining what reality means. Let's get specific about the numbers and see just how precisely this cosmic speed limit operates. The speed of light in a vacuum is exactly 458 meters per second. Notice that this isn't a measured value anymore. It's a defined value. In 1983, the International Committee for Weights and Measures decided to define the meter as the distance light travels in 1,299,792 4/8 of a second. This means that the speed of light is now exactly 299,792 458 meters per second by definition, and we use that to define what we mean by distance. This definitional shift reveals something profound about the nature of physical reality. We used to think of space and time as absolute background stages where physics played out, and we measured the speed of light against that absolute backdrop. But Einstein and Feynman showed us that it's actually the other way around. Light speed is the absolute reference, and space and time are relative measurements that depend on your motion through space-time. The cosmic speed limit isn't a speed limit in the traditional sense. It's the conversion factor between space and time, the fundamental constant that determines how many meters equal 1 second of light travel. When you're driving your car at 60 miles per hour, you're moving at about 0.6% of light speed. When the International Space Station orbits Earth at 17,500 miles per hour, it's traveling at roughly 0.26% of light speed. Even our fastest spacecraft, like the Parker Solar Probe that will eventually reach 430,000 miles per hour as it approaches the Sun, only achieves about 0.064% of light speed. These speeds feel enormous to us because our everyday experience operates in such a tiny fraction of the velocity spectrum that the universe allows. But here's what happens when you start approaching significant fractions of light speed, say 50%, or 90%, or 99%. At 50% of light speed, time dilation becomes noticeable. If you traveled for 1 year at this speed, about 15 years would pass for someone watching you from a stationary reference frame. At 90% of light speed, the effects become dramatic. Your 1-year journey would correspond to about 2. 3 years for outside observers. At 99% of light speed, time dilation becomes extreme. Your 1 year equals about 7 years for the outside world. At 99.9% of light speed, your personal time slows down by a factor of about 22. At 99%, the factor becomes about 70. As you approach 99% of light speed, getting closer and closer to the cosmic speed limit, the energy required to accelerate you further approaches infinity, while time dilation approaches infinite ratios. This is the universe's way of saying that the speed of light isn't just hard to reach, it's fundamentally unreachable for anything with mass. The closer you get, the more energy you need, until you would need infinite energy to actually reach light speed itself. Feynman understood that this wasn't a design flaw in the universe, it was the design feature that makes everything else possible. Particles with no mass, like photons, can travel at light speed because they don't experience the universe the same way we do. From a photon's perspective, the journey from the Sun to Earth takes 0 time and covers 0 distance. A photon emitted from the surface of a star doesn't age or change during its billion-year journey to your retina. It exists in a timeless state where departure and arrival are the same event. This is where Feynman's perspective becomes almost mystical, though grounded in rigorous mathematics. The speed of light isn't just a barrier that prevents faster-than-light travel, it's the boundary between the time-bound world of matter and the timeless realm of massless energy. When you understand that light exists outside of time as we experience it, you begin to see why the cosmic speed limit has the value it does. It's not arbitrary, it's the fundamental conversion rate between the temporal world of cause and effect and the eternal world of pure energy and information. Now let's explore how this understanding revolutionized our entire conception of the universe and led to technologies that define modern life. Einstein's famous equation, E=mc2, isn't just a statement about energy and mass. It's a revelation about the speed of light's role in determining the fundamental structure of matter itself. The c in that equation stands for the speed of light, and it's squared, meaning that even tiny amounts of matter contain enormous amounts of energy. A single kilogram of matter, if converted entirely to energy, would release about 90 petajoules, equivalent to the energy released by about 21 megatons of TNT. This insight led directly to nuclear physics, nuclear power, nuclear weapons, and our understanding of how stars generate energy. Every atom in your body was forged in the nuclear furnaces of ancient stars, where hydrogen nuclei fused into heavier elements under conditions so extreme that the cosmic speed limit became the governing factor in determining how much energy could be released in each fusion reaction. The light from those stellar furnaces traveled across space for billions of years at exactly 282 miles per second, carrying the energy that eventually allowed planets to form, life to evolve, and consciousness to emerge. The global positioning system provides another stunning example of how the cosmic speed limit shapes practical technology. GPS satellites orbit Earth at about 12,500 miles above the surface, where Earth's gravitational field is slightly weaker than at ground level. According to Einstein's general relativity, time runs about 45 microseconds per day, faster in the weaker gravitational field of satellite altitude. But the satellites are also moving at about 700 miles per hour relative to receivers on the ground, which causes their clocks to run about 7 microseconds per day, slower due to special relativistic time dilation. The net effect is that satellite clocks run about 38 microseconds per day, faster than ground-based clocks. This might seem like an insignificant difference, but GPS works by measuring the precise time it takes radio signals to travel from satellites to your receiver. Radio waves travel at the speed of light, so a timing error of 38 microseconds per day would translate to a distance error of about 11,400 meters, or roughly 7 miles. Without constant corrections for both special and general relativistic effects, GPS would be useless for navigation within days of activation. Every time you successfully navigate to an unfamiliar destination, you're experiencing the practical consequences of the cosmic speed limit. Particle accelerators like the Large Hadron Collider provide perhaps the most dramatic demonstration of light speed's absolute nature. The LHC can accelerate protons to 99.99991% of light speed, which means they're traveling just 7 meters per second slower than light itself. At this speed, the protons are moving so fast that they circle the LHC's 27-kilometer circumference about 11 Wouser times per second. But despite this incredible velocity, they can never quite reach the speed of light, no matter how much more energy is pumped into the acceleration process. What's fascinating is that these ultra-fast protons don't experience the 27-kilometer journey around the accelerator the same way we would. Due to length contraction, another consequence of approaching the cosmic speed limit, the protons experience the accelerator ring as being compressed to only about 7 centimeters in circumference. From their perspective, they're zipping around a track the size of a large coffee cup, not a facility that spans the border between France and Switzerland. This is the universe restructuring space and time to maintain the invariance of light speed. Feynman was particularly fascinated by what these extreme conditions revealed about the nature of mass and energy. As particles approach light speed, their effective mass increases dramatically, requiring more and more energy to produce smaller and smaller increases in velocity. But this additional energy doesn't disappear. It becomes part of the particle's total energy content, contributing to its gravitational effects and its interactions with other particles. The cosmic speed limit determines not just how fast things can go, but how energy and matter relate to each other at the deepest level. Modern telecommunications also depends entirely on the invariance of light speed. When you send a text message to someone on the other side of the world, That information travels through fiber optic cables as pulses of light, maintains its speed regardless of Earth's rotation, the motion of continents, or your own movement. The Internet works because light speed is absolute, ensuring that information transmission times are predictable and consistent, regardless of the relative motion between sender and receiver. But perhaps the most profound implication of the cosmic speed limit involves our understanding of cosmology and the observable universe. Because light has a finite speed, we can only see objects whose light has had enough time to reach us since the beginning of the universe. The cosmic microwave background radiation shows us the universe as it existed about 380 Ostwald years after the Big Bang, when it first became transparent to light. We cannot see further back in time because there was no light to see with. The speed of light creates a fundamental observational horizon beyond which no information can reach us. This observational limit has profound philosophical implications. There could be infinite numbers of galaxies, stars, planets, and even civilizations beyond our cosmic horizon, but they are fundamentally unobservable and unreachable because their light hasn't had time to reach us yet. The cosmic speed limit doesn't just constrain how fast we can travel, it constrains how much of the universe we can ever hope to explore or even know about. In Feynman's terms, we are prisoners not just of our local space, but of our temporal position in cosmic history. Yet Feynman saw this apparent limitation as another source of wonder rather than frustration. The cosmic speed limit means that when you look at the night sky, you're not just seeing space, you're seeing time. Every star shows you its past. Every galaxy reveals ancient history. Every photon carries information about conditions that existed long before Earth formed. The speed of light transforms every telescope into a time machine, every observation into archaeology, every measurement into a conversation with the deep past. Modern astrophysics has revealed that the expansion of space itself can actually carry objects away from us faster than light speed, but this doesn't violate the cosmic speed limit because space itself is expanding rather than objects moving through space. The most distant galaxies we can observe are receding from us at several times the speed of light due to cosmic expansion, which means their light is being stretched into longer and longer wavelengths as it travels across expanding space to reach us. We see these galaxies as they were billions of years ago, when they were much closer to us and space had expanded less. This creates another layer of the beautiful prison that Feynman described. Not only are we limited by light speed in terms of travel and communication, but the expansion of the universe means that most of the cosmos is already moving away from us faster than we could ever hope to reach it, even if we could somehow travel at light speed. The observable universe represents just a tiny fraction of what might actually exist, and that fraction is determined entirely by how long light has been traveling and how fast space has been expanding. Hey, if you're finding this exploration of the cosmic speed limit as mind-bending as I am, please hit that like button to help more people discover these incredible insights about the fundamental structure of reality. And if you want to dive deeper into physics concepts that challenge everything you think you know about the universe, make sure to subscribe and ring that notification bell. I've got so many more videos planned about the strange and beautiful ways that physics reveals the hidden architecture of existence. But let's return to Feynman's central insight about why this cosmic speed limit exists at all. Remember, Feynman wasn't just interested in what the equations predicted. He wanted to understand why the universe was structured this way in the first place. His answer was elegantly simple. The speed of light represents the fundamental rate at which cause and effect can propagate through space-time. It's not arbitrary, it's the consequence of living in a universe where logical consistency is possible. Think about what would happen if information could travel at infinite speed. Every event would instantly influence every other event throughout the entire universe. There would be no such thing as local causality, No way to isolate systems for study, no possibility of making predictions based on nearby conditions. The universe would be a single, interconnected web of instantaneous cause and effect relationships extending across all of space and time. While this might sound appealing in some cosmic sense, it would make the evolution of complex structures like stars, planets, life, and consciousness impossible, because there would be no stable local environments where organized complexity could develop. The cosmic speed limit creates what physicists call light cones around every event in spacetime. These light cones define which events can causally influence each other and which cannot. Events outside your light cone cannot affect you until their influence has time to propagate at light speed to your location. This creates islands of relative independence in spacetime, regions where local conditions can evolve according to local forces without being constantly overwhelmed by influences from distant parts of the universe. This is why Feynman saw the speed of light not as a limitation, but as the foundation that makes complexity possible. The cosmic speed limit is what allows stars to form stable fusion reactions, what permits planets to maintain stable orbits, what enables life to evolve over geological timescales without being disrupted by every cosmic event occurring throughout the universe. The beautiful prison of light speed is what creates the spaces of relative calm and predictability, where consciousness can emerge and begin to understand its own cosmic context. Feynman also understood that the cosmic speed limit reveals something profound about the nature of information itself. In our everyday experience, we think of information as something abstract that can be transmitted instantaneously. You think of a phone number, and that information seems to exist immediately in your mind. You tell someone a fact, and they understand it right away. But Feynman showed that even the transmission of information between neurons in your brain is limited by electromagnetic propagation speeds, which means that your thoughts themselves are subject to relativistic constraints. When you have an idea, that idea propagates through your neural networks at speeds much slower than light, but still governed by the same fundamental principles that limit communication across cosmic distances. The electrical impulses that carry information between your neurons travel at speeds ranging from about 2 miles per hour for slow nerve fibers to about 250 miles per hour for the fastest ones. These speeds seem fast compared to walking or driving, but they're infinitesimally slow compared to light speed. Your consciousness exists in a pocket of space-time where information transmission is dramatically slowed compared to the cosmic speed limit, which creates the subjective experience of having time to think, to deliberate, to experience the flow of time as a series of discrete moments rather than a single instantaneous event. This perspective suggests that the cosmic speed limit doesn't just govern physics and astronomy, it governs the very possibility of consciousness and subjective experience. If information could propagate at infinite speeds, there would be no such thing as the flow of time, no such thing as memory and anticipation, no such thing as the narrative structure of conscious experience, where thoughts and perceptions unfold in sequence. The speed of light creates the temporal spacing that allows consciousness to exist as a process rather than a single, timeless state. Feynman's final insight about the beautiful prison of light speed involves the relationship between knowledge and mystery. Every time physics discovers a new fundamental limit or constraint, like the cosmic speed limit or the uncertainty principle, it reveals both what we can know and what we cannot know about the universe. The speed of light limit means that there will always be parts of the universe that remain unobservable to us. Events happening right now in distant galaxies that we will never be able to witness. Civilizations that might exist beyond our cosmic horizon that we will never be able to contact or learn about. But rather than seeing this as a source of frustration, Feynman saw it as a source of perpetual wonder. The cosmic speed limit guarantees that the universe will always contain more mystery than any intelligence can ever fully comprehend, No matter how advanced our technology becomes, no matter how sophisticated our theories grow, there will always be more questions to ask, more phenomena to investigate, more connections to discover. The beautiful prison of light speed ensures that the universe remains an inexhaustible source of curiosity and exploration. Looking back at this journey from Ola Rimmer's observations of Jupiter's moons to our modern understanding of space-time, information, and consciousness, we can see that what started as a simple question about the speed of light became a revelation about the fundamental architecture of reality itself. The cosmic speed limit isn't an arbitrary barrier imposed by nature to limit our ambitions. It's the essential feature that makes existence possible. That creates the stable framework within which matter can organize itself into stars and planets, within which life can evolve and consciousness can emerge, within which intelligence can develop and begin to understand its own cosmic context. Feynman taught us that the most beautiful discoveries in physics are often the ones that initially seem like limitations, but turn out to be the foundations of everything we value about existence. The speed of light doesn't imprison us in a small corner of the universe. It creates the universe itself, defines what we mean by space and time, determines how energy and matter can interact, establishes the causal structure that allows complex systems to evolve, and provides the temporal spacing that makes consciousness possible. The next time you use GPS to navigate, or send a message across the internet, or simply look up at the stars on a clear night, remember that you're experiencing the practical consequences of the cosmic speed limit. You're living inside the beautiful prison that Feynman described, surrounded by walls that seem to constrain but actually enable, confined by limits that turn out to be the very foundations of freedom, mystery, and wonder. The speed of light isn't what prevents us from exploring the universe. It's what makes the universe worth exploring in the first place. Note, this script combines educational physics content with narrative elements designed for entertainment and engagement. While all scientific principles discussed are accurate, some historical scenarios and detailed personal perspectives attributed to Feynman represent educational interpretations rather than documented statements.